And welcome anybody who's out there and who's listening. This is our second mathematics curriculum convo with myself and with Lucy, and we're joined by our special guests tonight. That's Rhiannon and Sharon and Jane and Mr. Kit and Jen. Would you care to just introduce yourselves a little bit and a little bit about yourselves? Rhiannon, do you want to?
Hi, I'm Rhiannon Rainbow. I'm the School Improvement Lead Maths for the Greenshaw Learning Trust, and I started my teacher training as an early years primary maths specialist. So it's been quite a journey.
Oh, we could have done with you last week.
Hi, I'm Sharon Malley. I'm curriculum leader second time round, so I've stayed in middle leadership twice for some reason. And I am in Leicester at Catamouth Academy, leading curriculum there. So we're a free school, so we've got year 7 and 8 at the moment, going into year 9 next year. And once upon a time, I'm going to get it in, Pete, I was PCE mentor.
It's the only reason she gets anywhere near this stuff now is because I let her in.
Well, now I know she's got some dirt on you. I bet. Yeah, never mind letting in. I think we know where the power is in this relationship, Pete.
Oh, 100%. 100%. Jane, thank you.
Hi, I'm Jane. I'm a secondary maths teacher down in Devon, and teaching for mastery specialist for the NCTM Maths Hubs.
Brilliant, thank you, Jane.
Hi everybody, I'm Kit. I am from the other side of the ocean. I'm based in New York City, a public middle school teacher for the last 11 years with Math for America. And I've taught kids who are struggling with division my entire career.
Very nice. Nice to get the content in early doors, Kit. I like it. And Jen, finally.
Hi, everybody. My name is Jen Hill Parker. I am an essay leading in Salisbury. I was a head of math for a long time, and now I'm working with the NDTM as well, and the SLE for Maths Across the Math Hour Trust.
Brilliant. Thank you very much. And we are here to discuss today division. And why is it so blooming hard?
Oh, blooming's allowed, is it? You're making up the rules now.
That's definitely not a swear, Lucy.
Well, yeah. Come on.
Why?
Oh,
now, I remember...
Define a swear for me.
Oh, really? We'll come back to that, Lucy. Well, maybe when we're off stream, we'll have some examples, because I think the best way to define a concept like that is with examples and non-examples, and I don't particularly want to put all those examples all there. Yeah, boundary examples, things like that. So, what was I going to say? I remember quite a few years ago, Anne Watson describing division as the dragon that kids have to slay in order to progress in maths. And that sort of, I always keep coming back to that. So, come on then, guys.
So what's the treasure if division's the dragon?
Who said there was treasure?
Well, this is a metaphor, right? And one would assume that in order to slay a dragon, you get somewhere, and the somewhere is usually the place where the treasure is, right?
Yeah, so the somewhere...
there's something to rescue.
Well, I think... Yeah, I mean, if we start going in that direction, it gets a bit anti-feminist.
And aren't dragons magical and beautiful creatures?
Right. Should we be slaying them at all? Great question. Love it.
Well, I don't know. Take it up with Anne. It was her metaphor. So, what do we think, guys? Why do kids find division so hard? Kit, you mentioned, first of all,
I think
you've been teaching kids that struggle with division all the time. So why don't you start us off?
Sure. So I think a piece of it is that a lot of students are stuck in thinking additively where they're like able to count or they're skip counting. And so even though they might appear like they've got their multiplication facts memorized, it's really just that they've gotten good at skip counting. They don't have that deep conceptual understanding of multiplication. So to be able to undo it and reverse it, it's far beyond what they can reach easily.
I'm ticking off a list. I've got 8 in front of me, and you pretty much covered 2 there. So.
Oh, 2. Which 2, Lucy?
So of my list of 8, I had one which is that people can get away with using procedures of repeated addition for multiplication, but it doesn't help that understanding, that deep understanding of related concepts, and therefore when you move to division it's problematic. Exactly what you said. And then if we're too fast to memorize times, tables, facts, there is a sense there that students haven't got the kind of concrete and representational experience of multiplication to understand it, to be able to invert it. So perfect, love it.
Lovely. Sorry, Sharon. Jen, you were going to come in and say something at the same time that Kit did.
Sorry, yeah, we were speaking at the same time. I was just going to say, in my experience, that students understand what division is. They don't understand, and I think, you know, in the early stages you can create the fact families with, you know, the multiplication. 3 times 4 is 12. 12 divided by 3 is 4. And that can work quite well. It doesn't translate up as the students sort of get a little bit older and they need to apply that process to more complicated problems.
We'll perhaps come on and talk about what division is then in a little while. I love that Lucy's giggling there. Sharon, what were you going to say?
Well, I was going to say, I actually think it's part of sort of human psychology as well, that we actually, if you look at the language we use, we do actually work quite multiplicatively in our way we talk. This is 2 times bigger, that 3 times bigger, but actually formal maths then starts with lots of adjectives, as Kit said. So when you're comparing, you're looking how many times bigger it is, and we get that idea in a sort of a what Geary would say was that biologically primary fault maths idea, that things are this many times bigger. But the reverse of that is much more of, well, how many times smaller, or the inverse division. It doesn't intuitively respond. We actually do work multiplicatively, which I've said so many times. I find that such a difficult word to say. More than we do divisively. I'm not even sure that's a word. Lucy, tell me if it's a word.
I've literally said that sentence. I was interviewing Margaret Brown about this, and I literally said divisibly, divisibly. She went, I don't know. No one knows. It doesn't matter.
We don't even have a word for it.
I think it's a perfectly good word, whether it's recognised in the dictionary or not. I think if you said divisibly in that context, everybody would know exactly what that meant. So I think you're fine there. Jane, you wanted to come in?
Yeah, it was about language as well, really. I'm really interested in the way we talk about maths, kind of our internal dialogue of maths, but also how we communicate with each other, teacher to student, and also peer to peer in student groups. I think the language we use is really important and really powerful in terms of making connections, but also kind of securing that understanding, learning through talk, and so being able to explain their mathematical thinking. And I think division is something that we talk about really poorly, a bit like Sharon's saying, like the divisibility thing. But I'm increasingly trying to make sure I'm using words like dividend and divisor and quotient and labeling these parts so that my students and I can engage in this dialogue about what we're doing, being able to label the parts.
Right.
Cool, thank you very much.
I did want to say something about that, because when I was teaching, it wasn't usual to use those words. You know, this was some time ago, and my children are going through the system now. They're both in secondary, and so it is interesting to me that the use of those words is quite widespread, and I don't have any particular problem with it per se. I find perhaps it's unnecessary to use those particular words, because the thing to me that is being referred to is not necessary. you don't necessarily fix it by using those words. You can, but it's not a sort of sufficient condition to use the words to fix the thing. And the thing for me is what makes division so hard is my number 3 reason, but I think it's probably actually the most important, is that it's a binary operation instead of a unary operation, which is the thing that took me ages to get my head around. But now I think, oh, that's the thing. So instead of and multiplication is too, to be fair, but there's other issues with multiplication. So when you're adding and doing something unary, essentially the two things that you are operating with are of the same kind of element. But with division and multiplication, it's not the same kind of thing. And so I think it's exactly as Kit said. With multiplication, kids can get by without thinking of it as binary in lots of ways. And they don't often have that sense that there is it's a size of a set and the replications of that set. So those two things are actually different. Because it's commutative, sometimes we kind of just treat them as the same, and that's fine. But then there's that symmetry to multiplication. As soon as you get into division, the symmetry is lost. We've now got 3 parts going on that we can't just rearrange and play with in the same flexible way. And so I think using that language is maybe an attempt to make those things more distinct, which I think is great, but you don't have to do it that way. I'm not sure if that was clear. I hope it was.
No, absolutely. Kit was definitely sort of making lots of hand gestures to follow on there. Kit, do you want to add anything to that?
Yeah, well, I was thinking about this because this year with my 6th graders, we've been doing fraction division, which of course is like the most complicated of complicated divisions. And yeah, and one of the pieces that is so tricky there is what Lucy was just saying about how now the order matters. And, 6th grade, we're really starting to think about proportional reasoning. We're starting to think about ratios. And the ratio, everything is important in terms of the order. And I really think about the connection between division and ratios. So when earlier somebody was saying like divisibility thinking, I think it's rational thinking, right? But that word just sort of doesn't flow as well. And I think that this idea that like one of the factors is about the amount of groups and then the other factor is about the size of the group. And when we talk about division, the divisor could actually be either of those. And so it's sort of like this weird role where we lose some flexibility in terms of we can't rearrange the order, like the divisor and the quotient can't just be switched, but the dividend and the divisor, I should say, can't be switched, because you could switch the divisor and the quotient, which is, right, like that's weird, that's different. It's now on the other side of the equal sign. So it's sort of like the pieces that are move in a different way, and they're sort of mysterious because we suddenly use different language. In multiplication, we're talking about 2 factors and a product. Now suddenly we're talking about a dividend, a divisor, and a quotient. Yeah, sorry, I lost that one.
That's all right. Does this oh, go on, Sharon, you go.
So do you think part of this is because we moved to what you might call naked numbers too quickly? So it's not 3 meters multiplied by 2, it's 3 multiplied by 2. It's, we lose what's actually happening to objects, to real things very quickly with multiplication, so that it's much more difficult. So it becomes 3 multiplied by 2 is equal to 2 multiplied by 3. Well, actually, if you've got a stick 2 meters long and you've got 3 of them, that is different to having a 3 meter long stick and 2 of them. You end up with the same result, but it's not the same multiplication. And we lose that really fast in multiplication, which then I think makes it very difficult to bring back in for division.
I agree. I think I am not careful and considered enough in whether I'm considering looking at my division as sharing or grouping. And if I'm not considerate, if I'm not conscious of that, and if I'm not articulating that, I'm not modeling that to my students. So I'm not demonstrating that there is a difference and that it can be thought about in these different ways. And I think that's a big difference, because I know we're talking about difference and we're meant to be talking about division, sorry. But if we so much time is spent on number bonds, that's your addition. So much time is spent on times table facts, that's your multiplication. so much time is spent on the visuals and how different ways of representing multiplication. The division's just assumed, it's just the inverse. Here's a process that you can use, without the same amount of time and emphasis on what it actually is. And I think, so in my big history of maths book, this isn't a new thing. They've got, from the 1600s, they said that division is esteemed one of the busiest operations of arithmetic, and such as requireth a mind not wandering or settled upon other matters. So there's so much going on with division, so many different things, that you can't think about anything else. And Jo Morgan says, she quotes Pacioli, 1494, that if a man can divide well, all the rest is easy, for all the rest is involved therein. So I wonder, is division hard because we're focusing on the easy bits and we're not focusing on division? And I just, sharing, grouping, all of these different names, quotient, divisor. I only used the quotient when I started teaching A-level with the quotient rule, and then trying to do algebraic long division. In between primary and year 13, I hadn't taught it to my students. So my emphasis is wrong. And I wonder if that's where we go wrong with division, because we just teach a quick process and it's easy to forget actually what they're doing. Sorry, but yeah.
Well, I just have 1 second to do an eye roll for the use of man there. Okay.
I think also,
that's fine. Move on.
There's a different notation used when we're doing division. So we can do 20 over 4 as a fraction, as it were, and we teach them that means divided by. We've got the use of the division symbol, 20 divided by 4, and then we use the bus stop as well. And I think that the use of several different symbols to mean the same thing, just following on from what you said, Rhiannon, because you said about sharing and dividing, and I think that it is one of those areas of mathematics where there are multiple ways of using the symbols, using the words, and that can cause difficulties to creep in.
And I think we know how to use them, and we think we know. I think I know how to use them. I understand it's a process. I'm not understanding the mathematics behind it, and I'm swapping and changing between them, but I'm not explaining to the students how and why I can swap in exchange between them, and what the differences are with how some can be used in certain ways and some are easier for different things. I just swap and move them around all the time without being explicit enough about what I'm doing. Sorry, Pete.
No, not at all. So we've had a comment come through from Vicky Osborne, who was one of our guests last time, and that actually links nicely with what Kit was saying, what other people are saying. So she asked, do you think dividing with fractions is so difficult because it can be thought of as because it can't be thought of as sharing? And I was listening to things about grouping and sharing, and for me, neither of those are complete models of division anyway.
So
in terms of, there are divisions that can't be made sense of to me, certainly intuitively and easily, when we try and think of them as grouping or when we try and think about them as sharing.
Can you give an example of that, Pete?
Yeah, so classic example, 20 divided by -4. You can't share 20 into -4 shares. Really, it doesn't. You look at that, it doesn't add to your for me, it doesn't add to your idea of why that would be -5 and why that would come out as -5. But in the same way, if I ask a kid to create groups of -4 from 20, that's not intuitive either, and that doesn't seem to sort of make sense with how division, how I've met division in the past.
That is a context-free negative. I think that's a very sneaky context-free negative, I'm going to say. Because the question here about dividing with fractions, it's almost impossible to think of it as sharing short or without context. But if you have a good context, I think you probably can. And I probably think that with the negative example to some extent. I think it comes back to Sharon's naked numbers idea to some extent, I think.
So what do we think about this fractions then? Is it because it can't be thought of as sharing, and sharing is perhaps our most natural way of thinking about division? Kit, you want to come in on that, and then Jane afterwards?
Yeah, I disagree. I think that you can think of fractions as sharing. I say that because I literally just taught my students fraction division with sharing. For example, if I'm thinking about, I have 3/4 pound of almonds and I want to make little baggies, and I'm just going to use a really easy one for the moment, right? That each bag contains 1/4 pound of almonds. How many bags can I get? I can get 3 groups, right? 3 bags. And I can also, like in that case, right, I came up with a nice easy set of numbers so I'd get a whole number, but I could also still wind up with not so nice numbers that are going to give us a fraction in the end. And I've seen kids like struggle to interpret that remainder when there's that fraction left over of like, wait, so the original thing was 3/4 and that one group is 1/4, but it's a half of the size of the group, and right, and then they get all confused because there's too many fractions there. And I think that the piece goes back to, I forget who said it earlier about the like 2 quantities. With division and with ratios, it's the first time that you're really required to track 2 things at the same time. You're not just thinking about 1 quantity, you're thinking about 2. And so fraction division, you're now suddenly thinking about 4 quantities because you're thinking about the 2 quantities in the original fraction and then the 2 quantities in the second fraction. And so now suddenly you've got 4 quantities to keep track of instead of just 1.
So actually, in the example you gave, in this country, we would normally talk about that as grouping, of creating groups of a certain size, rather than sharing, which would be, you know, split it into this many shares. And in your example, you know, 3/4 of a pound of olives, split that into a quarter number of shares, which intuitively wouldn't make sense, whereas create groups of size 1/4. But I think this is part of it as well. I think this language, because people say share into equal groups.
Right.
Well, and that to me is nonsense.
Right.
Share into equal groups. Which model are you using there? I want to bring Jane in, sorry, because I said Jane could come in afterwards. Jane?
Thanks. I think part of the reason, or certainly in my teaching journey, part of the reason divisions of fractions is really tricky is because it's so easily taught with no understanding at all. I can, in 10 minutes, get kids to be able to do fraction division by just KFC, you know, do something, flip it over, and yeah, exactly. And then they can do it. And so I can teach that in 10 minutes and I don't have to think about them understanding it at all. And so I think that's quite common practice. I think it's becoming less common, but I think it has been fairly common practice. And so some of the teachers who are now teaching were taught to divide fractions by keep it, flip it, change it, or similar. And so actually our own understanding of dividing by fractions isn't as deep and secure as it should be. So we revert to teaching with a method that doesn't require any understanding. Because if I teach for understanding, I have to really, really understand it. I have to understand it in backwards, forwards, left and right, so that when a kid asks me, I know where they've come from, I understand where their misconceptions have come from, and I can address them because I'm confident in my own subject knowledge. And if you're even a tiny bit not, then doing it with a method is just way safer.
Sharon, you were going to come in on something, I think.
No, I was just going to agree. I think we would just hope there's been a large generation of maths that was taught as a purely process, and it's only if you really take the time to go, why is this happening? How is it happening? How is it connected to what else I know, that you actually get into that we've got this subject knowledge gap there, and we're filling it ourselves and through things like the NCTM and Mastery, but it's very patchy. So you've got patches of good practice and you've got patches of poor practice. We're trying to work with that at the moment.
Well, but I was just thinking one way to conceptualize that, and I feel that to be true as well. One way to conceptualize that sort of patchiness is also to say that there's a lack of connection, because it is not just, I don't really understand division particularly well. It's actually, I don't understand how division relates to other things. And I was thinking about what you were saying about measurement, because one of my I've got 9 actually now, I wrote down another one. One of my 9 points, that it's you have to develop an intuitive sense, which is really hard, that the greater number of parts that you divide the whole into, the smaller the size of the parts. And that is a measurement issue. And that sort of units coordination issue of dividing into, well, if I've got smaller parts, there's more of them. If I've got bigger parts, there's less of them. And what's the whole? You know, what Kit was talking about in terms of, you know, if I start with a fractional whole, well, that's mind blowing. But actually, if kids are really used to being flexible with the way they conceptualize the whole in measurement, suddenly we haven't got such a massive problem. But connecting division to measurement, and then also connecting that across to some sort of abstract number properties, and then also connecting it to data, because we shouldn't forget about data here. Data is really important in division. You know, the number of groups that you choose to display your data in is crucial, and that's a division issue. And then finally, we also need to connect this to ideas of fairness, which is an ethics issue, because how can we talk about being sharing and equal and fairness without thinking about actually human context? So, you know, to some extent, it's not just about subject knowledge in a very divorced way from context or across. It's about real deep, lovely connections.
I wonder if picking up on what you've said there, Lucy, and also what Sharon said about the fact that we've got a generation of people who've been taught the process. And I think that's most likely why. You know, I love maths. I couldn't do my job if I didn't. But I really like the abstract maths. I really like it when it's just the processes and the algebra and you're just manipulating it and playing with it. When it comes to actually applying it, mechanics, even decision maths or statistics, I find that quite a big leap for me. And I have to work really hard to make those deeper connections, because I'm just used to the maths, what you people might think of as the maths, because that's what I was taught. I was just taught the processes. I don't remember, should I say, being taught the deeper understanding.
Thank you. Julia's commented, or Tessmass commented, stacked fractions is the best for division. Links well to division as a fraction. And I'm assuming that stacked fractions are one fraction on top of the other. Is that what we think? Has anybody looked at it like that, or has anybody got a different sort of idea of what that might be?
No, I assume that too, fraction walls.
Okay. Jane, you've got something in there?
Are you looking at, sorry, I lost half your sentence. Are you looking at the Tessmass comment about stacked fractions? Yeah. I don't know if Tessmass can hear us. Do you mean like a fraction over a fraction for fraction division? Or someone just said fraction walls. Sorry, I missed half the sentence.
Hopefully she'll come back to us on that one and provide a bit more context as to stacked fractions. She's also said this. We have division as fractions and in ratio tables. Can't we simply abandon division? And you hear this from some places. I hear it more with subtraction, actually. You know, that subtraction is just adding the negative. And so actually, we don't need... Well, that was fun. We don't need to... we don't need to consider subtraction. It's a superfluous operation. The same could be said for division, because it's multiplicative, you know, multiplication by the reciprocal. Jen, any thoughts on this?
I think I was actually going through this with my year 11 in the past paper. The question was something like 24 divided by a half, and it's a low set that I teach, and so we just went through some known. We went through 24 divided by 12, and we know 2, and we know that we can reverse the way we explain that to say that means 2 lots of 12 is 24. And we're happy with that, and that's something we've been comfortable with for a little while. And then move on 24 divided by 6 and 24 divided by 3. Just keep changing that number, and then start 24 divided by 12 is 2, and that means how many 12s do you need to make 24? and we know the answer is 2. 24 divided by 3 is 8. So how many 3s do you need to make 24? And the answer is 8. And then when we got down to 24 divided by 1, 24 divided by a half, we always went about fractions with this particular club about either pizza or cake. So we're thinking about pizza into halves and how many would you need in order to make 24 whole pizzas or cakes. And they came up with that notion of multiplying by have the process of making that number dividing by smaller and smaller and then going into fractions. And we extended it a couple more times, 24 divided by a tenth and so on. So I personally, I was taught KCF, the Keach Flip. I used it for a long time and I just use that again. Unless it's obvious that they came up with that themselves, in which case we can remember the process by, using these letters. But I think it has to, for me, it has to, in order for the understanding to thoroughly be there.
See, we've bumped into the Gazinta bit now, haven't we? I was wondering when we bump into Gazintas, how many R's goes into 24?
Pete, I do have Joan's book here if you want to see what the stacked fractions example is.
So Julia has actually been on and said, yep, in Joe's book, which I think
have it right here.
Confirming it is that one fraction over another. You now maximise your Lucy. Here we go.
Oh, sure.
Get it up to 10.
How's that? Useful? So, yeah.
Yeah, kind of. I think it's bottom bit here, isn't it? Yeah, one fraction over there. Yeah, that looks good.
Yeah.
We can't make out the text, but I think we can make out the shape.
No, I can see it. So you do the stacked fractions, but then you have to basically, it's a little bit like rationalising denominators. So you need to then make them into units by multiplying by the denominator of the fraction by so you're unitising the two parts of the fraction.
Yes.
And Joe makes the connection to the ratio table use there, which I think is really helpful as well. Yeah.
Yeah. Kit, you wanted to come in? Oh, this is Joe Morgan.
Oh, okay. Yeah, I had another thought about the question that somebody posed. I think it was Test Maths, saying we have division as fractions, and in ratio tables, can't we simply abandon division? And I'm not sure how you abandon division when you're thinking about fractions as division. And I feel like I wonder if a piece of that question might be, can't we simply abandon the long division algorithm? Which, like, that question I'm in favor of. Yes, let's abandon it. Because I do think that, ratio tables are a really helpful way where you can think about, unit rates are what fraction division is, right? You're always trying to find out how much per one of the denominator. And so if you start organizing it in a ratio table, then suddenly that connection becomes clear and you're doing a lot more scaling with multiplication and you're not thinking as much about division, even though you're still kind of doing that. But I also think that there's a model that we haven't talked about at all really yet, which is the area model. And I think that the connection to the distributive property is such a powerful one for understanding multiplication that we don't emphasize enough. So when kids get to division, they have no idea how to use the area model or the distributive property to help them with division. And when you think about being able to look at a number and like split it into friendly numbers for division, you're really just applying the distributive property again.
But it only works one way. That's the problem. I'd suggest they do try and use it, but they overuse it.
What do you mean it only works one way?
So this is another one of my many points about division.
We've gone from 8 to 9 to many there, have we, Lucy?
Yeah. So thinking about what you were saying there, I think distributivity is one of the hardest properties to get underneath for me, thinking about the way that numbers work. But once you have somehow started to grasp it with multiplication, the idea being that you can then sort of partition the multiplication either way. So I was reading a paper just about this today, and the example was that if you have 7 times 12, you could partition it into 7 times 4 plus 7 times 8. Nice. But you could equally do the 3 times 12 plus the 4 times 12. And so you can do that in a kind of symmetrical way, which is quite pleasing and gives you lots of flexibility with choices. That it breaks with division, and it's not immediately obvious why, I think. So if kids try and do an 84 divided by 7, they might realise they can do a 70 divided by 7 plus a 14 divided by 7, great. But they also often will do the 84 divided by 4 plus the 84 divided by 3. And so I think the overuse is sometimes the issue, not necessarily that they don't understand it, they just apply it to everything with great eagerness.
Well, and that's why I think rooting the distributive property in the area model is so important.
Right.
Because if you understand that the product becomes the dividend, right? And then you understand that the area of this rectangle is what you're trying to sort of divide up, and you know one of the dimensions and not the other one, then it's a lot more meaningful than just sort of playing around with the distributive property and how am I splitting these numbers?
Understand area as a concept and dimension as a concept, and both of those are really hard.
Right, but I think those are underutilized. Sorry,
But this means
Go on, Sharon.
we shouldn't call it a bus stop. We should just draw it as a rectangle.
Well, this is the point I was going to make, because Kit was saying, quite happy to get rid of the long division algorithm, but obviously the sort of root of that is rooted in the area model, in terms of that's where that sort of shape comes from. We have one dimension, we're trying to find the other one.
I'm not having it. That's a very oblique reference, and kids don't get that, do they? Never. Why would
they do if you show them. My kids love it. I show them it in year 7, and they see.
Right.
I show them. Oh, look, we had this area where we did a 7 times a 12, and it was an 84. And what I'm doing now is I've got the 7 and the 84. What goes on the top?
Sure, but I think you can have all of that area model partitioning stuff without the bus stop. You can connect them if you want to, but I don't think it's necessary for that. You can do that reasonably without it.
I think the algorithm is sometimes one of our biggest issues, and because in the UK of that real push in Key Stage 2 to really make sure they've got the algorithm nailed, I think that division in some children's heads becomes the algorithm. It's all there it is, and I have to say, we try to teach it as a remote lesson, a videoed remote lesson of revision, and it is the most difficult thing I have ever tried to explain properly. Exactly, because number one, you work left to right, not right to left, and you start with the largest numbers first, and you're dividing that for a very good reason, but you've got everything that you normally do with place value, with addition, with subtraction, totally different. You've got to really explain what you're doing, that you're taking out groups of this, that your remainder is going here, that it's being exchanged to the next place. There is so much complexity to it that I am sure that most people don't even try to explain any of that. You just go, this number here, right, that, and it there becomes a massive magic bit where numbers are popping out of everywhere and other numbers are going in, and people just, you either know or you don't know.
I think this is probably why Anne called it the dragon, to be fair.
Yeah.
I was just thinking the same, especially when Test Maths says that it's called the sleigh method in Sweden. It's a really dodgy segue there, isn't it, to slaying a dragon?
Oh, nice punning. I enjoyed that.
Yeah, that's nice.
Yeah, so I think it's true to say that the algorithm is has quite a lot of complexity. It's really easy to get wrong, and is a proxy for division. And in this country, it's an emblematic political proxy for being good at maths in a very odd, very fetishistic kind of way. But yeah, I think it leads into other arguments about algorithms, which is that on its own there's no particular issue with it. It's the way that we focus on it, and also if it doesn't emerge out of children meaningfully trying to invent their own representation, then they don't see the point of it, or really why, like, what are we using that? Well, it's a general standardized communication tool. It's not just, it's a process, it's a way of communicating your thinking. Well, if kids can invent other ways to do that they like more or is more interesting, at some point we need to give them permission to do that. And that again comes from national curriculum being overly prescriptive, I would imagine.
Dead air time there. With,
yeah. Everyone's like in their head, standing ovation.
So we did have a little bit earlier on the start of a tweet from Mr. Gaskell, Mr. G teacher, common misconceptions writing, and he stopped it there, but I picked it up in another thread on Twitter, which was basically getting the dividend of the divisor the wrong way around. So wanting to do 6 divided by 2, writing 2 divided by 6, potentially also getting the correct answer from that though, and still being able to write down 3. So where is this a problem? Is this a problem? What what causes the problem? What is the solution potentially to the problem? Anybody want to come in on that?
I'm interested in Kit's knowledge of working on the other side of the pond, because I keep thinking about the fact, did we do something really bad with decimalisation, and therefore we stopped using fractions for a lot of things because we went to decimals? And so many children want their answer to either be a whole number, an integer, or a decimal, but they do not want to leave their answer as a fraction. Are kids in the US more comfortable?
The same. No,
The same.
they have the same exact problem where they're like, it's not done if it's a fraction. And I think that part of it is that in elementary school, you know, they keep going with the division until it's, like you said, a whole number or a decimal, but they don't even know how to deal with a fraction like 1/3 that goes on forever in the decimal expansion. And so they get very confused there. And I think that a piece of it is about the disconnect between notation and the way that we talk about it, right? If I say, we're going to divide this in half, that's different than if I say, we're going to divide this by half. And that's one little itty bitty word, by versus in. And especially if you're a student who is not fluent in sort of the English of math, right, then you're going to miss that nuance. And I think that that's a big piece of where we get into trouble with division, is that the flexibility that Lucy was mentioning earlier that we have in multiplication with the symmetry, it doesn't matter. But we see this in both subtraction and division, where it's like, 5 minus 3, well, that's subtracting 3 away from 5. Wait, I just went backwards in my sentence. How do I know which order is which? And there's no sort of grounded, clear understanding for kids about how do I figure out the order that the things get written in if it doesn't match what I'm saying.
And in common culture, we use halves to mean loads of different things. We don't always mean one whole divided into 2 equal pieces. It can be any kind of split with 2 without it actually being equal quantities, and actually with my own young children, they like fairness and they like equity, but my child told me that if I cut an apple in half, I would get 2 pieces and I would not have half because I'm getting 2.
Yeah.
Well, and I think that goes back to the unit, right? The unitization of like, what is the whole? Are they right that you get 2 pieces? Absolutely. Because the piece is now their whole. But if you're talking about the half, well, you're thinking of half an apple. And that flexibility of shifting and changing what the whole is doesn't come up until we start getting into fractions and division. And that, I think, is a big piece of where we lose kids.
Unless we make it come up earlier on. And this is the thing for me is, and people will know this is why I sort of started pulling at the thread about grouping and sharing earlier on, because for me, comparison and the comparative model is that overarching model for division, and comparing two numbers, reducing one of them to the unit to 1. How does that compare to the other one? That sort of ratio and proportional division idea is the complete model for division, as far as I'm concerned. It does allow things like 20 over -4. Lucy's going to have some fun with me in a minute because I'm committing passionately to a bit here. But it does allow us to think about 20 over -4, because what if -4 becomes my whole? And, I can think about that. I can consider that in terms of rotation around a number line or whatever else. And I haven't yet found a division that I can't make sense of by comparing two things. But that takes me back to what Sharon and others were talking about earlier in terms of units, because then I'm thinking about, okay, well, what if I'm not taking 3 meters and multiplying it by 2 and repeating it twice? What if I'm creating that 3 meter by 2 meter space? And what if then later on I'm comparing a 3 meter length to a 2 meter length multiplicatively rather than additively? And then the division is a pure number, because it is literally just how many times bigger in effect. So the result of that comparison is unit free. There is no unit attached to that.
I think it's,
and Lucy's going to come in now and sort of destroy everything.
I'm struggling a bit here, because I think it's part of the problem is we're talking about abstraction and context, and it's almost like the point is to be able to abstract this as much as possible. And I fundamentally disagree with that. And one of the things that I disagree with is saying that the more abstraction we can do here, the more advanced and developed student thinking is. And I think, it's fairly clear that that seems to be something to question, but also student thinking is never advanced and developed here. It's really bad. This is a terrible area for nearly all of us. And so something, for example, we haven't mentioned yet is the mean. So thinking about, the unit per some kind of rate, well, that's what the mean is. And a division structure underneath the mean is absolutely crucial for lots of different things. And what would happen if we just taught the mean algorithm? Well, we know, because we do, and it's terrible. Students don't have that sense of, per unit, per person, per thing with the mean, and then they can't see it as that kind of single sample, spread out, shared, all those lovely models that like richness underneath that. So I guess that's what I'm arguing with, Pete, I think it's about reducing dimension then, not necessarily not taking out a unit, because I don't think a unit for me is about measure. A unit for me is just about a sense of what the whole is. It can be abstract.
Yeah, but that surely in terms of that division, then that is unit free in terms of if your unit is 4 and you've got 5 4s and you divide by 2 4s, you have 2.5. You don't have 2.5 4s. Your unit is gone.
But you were talking about comparing being crucial for you, and if you're not comparing to what you started with at any point, you don't have to. But if you're not, then where's the value? What's the point of it?
So the point is to sort of establish that ratio that applies no matter what the unit. And that for me is where that thing. Now I'm not saying it's the only model we should use.
You're not seeing the ratio of the unit.
Right,
that's what I'm asking. What about the ratio being a unit in itself? That's the question I'm asking you. I'm not necessarily thinking of a unit as an input. I'm thinking the ratio could be considered a unit.
So what would the unit be in that sense then?
Give me your example again.
So I have 2 lengths of 4 meters.
Yeah.
And I have 5 lengths of 4 meters. So 5 sort of lengths of 4 meters.
Of what?
Wood.
Yeah, wood, whatever.
Okay.
And I am comparing that to 2
So
lengths.
hold on, you're saying Pete's got wood.
Oh, thank you. Let's just descend this into the toilet.
Just need to check, yeah.
So I have 5 4-meter lengths of wood.
Got it.
And I'm comparing that to the length of 2 4-meter lengths of wood.
Yeah.
And I'm comparing them multiplicatively. And
yeah.
the first thing I have is 2.5 times bigger than the second thing I have, and that doesn't matter.
I don't understand what the thing is that you have.
The length I have here. So
why have you got 4 of them?
Sharon,
I don't.
stop.
Each one is 4 meters.
But you've got multiples of them.
Yeah, I've got 5 of them.
Why?
Oh, for giggles.
I'm really struggling with the motivation for what we're doing with this mathematically. I'm honestly, I'm not winding you up. I really want to know what the point is because it matters to me.
Because we can.
Okay, but so we've got. I don't understand why you're comparing a collection of things that have length to another collection of things that have length. Are you arranging them in a particular way?
No, I just want to see how. I just want to see how many times I'm creating 2 lines. I want to see how many times longer the top line is than the bottom line.
Right. Okay. So it's just about length. It's not about area at all for you.
Not in that context.
Okay. Yeah. Got it.
Yeah, and so the point being is that the top line is 2.5 times bigger than the bottom line.
Yeah.
But that it doesn't actually matter if if we consider those as 4 meter lengths, or if we just consider those as lengths, or if they were a different number, that unit of 4 wouldn't be there anymore. It doesn't matter that unit was there. It's now free of that original unit.
Is that just because you can simplify that ratio down to 5:2?
Yeah.
So
and
if the pieces of wood are all 4 meters long, then you can still scale that back to a simplified ratio of 5:2. Or have I lost something?
No, it's exactly, and that's for me. That's the point, and that's the sort of, this is just 2.5 times bigger than that, regardless of any rate or anything like that.
I see. Yeah, but I come back to why you're doing it. You're examining a relationship there, and what's the point of that? What's that relationship telling you? Why are you interested in it?
Well, because I can think about it, and I'm interested in the things I can consider.
Okay.
It may not be a particularly interesting consideration, but I can think about it.
I'm struggling to. This is proportional reasoning, right? And the thing that I find hard about proportional reasoning is you are asking me to do quite a lot of hard mental imagery, visualization, thinking, enlarging, shrinking, scaling, and I'm thinking about a relationship, and that's really important. Why am I bothered about the relationship between these two quantities? Like, what's the motivation for doing that?
Why does
I
that happen?
really like the one between the moon and the sun. So I haven't got the numbers, but the diameter of the moon and the diameter of the sun is the relationship between the two of them is exactly the same as the distance of them from Earth, which is why you get the solar eclipse. So that's a really interesting comparative multiplicative relationship for me. When I found that out, that's why they exactly match up to get a solar eclipse. Mm-hmm. That's interesting, but in a classroom I can't even remember what the numbers are. They're very big. Do we need to use the lumps of wood to just get the thinking about them? But I understand what you mean there, Lucy, of what's the point.
Well, maybe I'm not even being clear. I'm not saying what's the point I'm not trying to challenge you. Engage students in real life context all the time. I'm saying, for example, the example you've given there it's really important because it's static. There's no point anytime soon that the moon's going to be getting bigger, and if it did, there's no reason why the sun would get proportionally bigger. So we don't have a dynamic relationship there, and that's what's interesting about that to some extent. And if I were writing a sci-fi novel and I wanted an eclipse to happen, actually knowing that is a static relationship and I could replicate it in a different way but keep that proportion, great. But that's the thing, it's not necessarily the problem context in detail, it's the type of relationship and the interesting features of those relationships. That's what I get underneath here.
What do you mean by the type of relationship?
So kind of like I said there, we are talking about division, so we're assuming that proportionality is important here. And so that's really hard to understand, and it's particularly hard when we're talking division because we have this thing of, if we have the bottom of the fraction getting bigger, we have other things getting smaller. So there's a sense of inverseness that sort of just comes out of division that is fairly mind-boggling. And so when I say relationship there, it is like, if I change this quantity in one way, what does it do to other quantities? And as you said, to some extent with division, we start to have more and more of those added in the mix rather than just the two that we might have had previously. And so, but I also care about the reasoning behind that relationship. I think it's really hard to do some of this mathematical reasoning without a context, because it doesn't make any sense without a context. You know, if I look at a relationship and I notice that it's inverse, great. But actually, if I have a context, I can talk about why I would expect it to be inverse too, and why I would expect that inverseness to persist despite many other conditions that are happening. And so I'm not arguing that maths has to be science. I hope that's clear.
Yeah. So maybe looking more at like indirect proportion in the, as you know, as speed increases, time decreases, the rate, is that a more interesting relationship in terms of why it's mathematically connected?
I think for kids, they have an intuitive notion of space and time that you don't have to teach from scratch. They know about running because they run a lot, and they know about distance, and they know a bit about time, but not a lot yet because that's really hard. And so getting a sense of how those three things are related in experiential terms, and then talking about the mathematical relationship, yeah, I would see a real value in that, I think. Yeah.
You know, and I think that what you're highlighting here, Lucy, it really reminds me of some of the work that I did at the Freudenthal Institute in the Netherlands 2 summers ago, and their realistic mathematics education concepts, because
surprised.
I really think that, like, when you are able to sort of understand the human experiences that make sense to be described mathematically, you understand why we even bother doing this at all in terms of math. And so if you're building on what students have experience with, then they've got a picture in their head. When students said to me in our, review today for the fraction division quiz we have tomorrow, I don't get it, I don't know what I'm doing. I said, literally, okay, let's read it again. Can you picture it? What's going on? Just describe the picture. And the problem, I think, is that we rush so much to these naked numbers that there's no picture. There's no blocks in their head. There's no Cuisenaire rods. There's no, jars or, like jugs of things being poured together. And I really think that a piece of it is that in elementary school, at least in the US, we're not spending enough time measuring. And measuring gets messy. And that messiness gives the kids experiences that, in the same way that kids do better in reading when they have more experiences with the world, I think kids do better with math when they have more experiences with measurement.
Jane, you were smiling there at something. Did something sort of come to you there, or was there something you heard that you liked?
The reference to Cuisenaire rods, just we've been thinking a lot about multiplicative reasoning, proportional, and I heard someone speak really nice about Cuisenaire rods, and just her disdain at the unit being labelled as 1, and everything going from there. So it was a smile at Cuisenaire rods, and how well they can be used, but how infrequently they are used, I think, in secondary broadly.
And so powerful.
I think Cuisenaire rods are perfect for comparative division. And for looking at division as a comparison, because I mean, you imagine the blue rod, which we would, we might potentially call 9 if the white rod is worth 1, and then you imagine the green rod, which is 3 if the white rod was worth 1, and then you say, well, imagine the green rod is worth 1. What would the blue rod be worth? And that is your division. Right there. That is 9 divided by 3 becomes 3, because the blue rod now takes on the value of 3. And that to me is so neat and nice and perfect. And I can apply that to pretty much any type of number. And I get what we're saying about rooted in experience and things like that. But for me, one of the beauties and joys of maths is it can take us beyond our experience, well beyond, and we might have to start where their experience is. I'm not going to necessarily debate that, but I want to take them beyond their experience. I want to take them into the realms of pure thought, the things that we cannot possibly actually do in this world, but we can only think about.
So thinking about, you're talking about the different colours of the Cuisenaire rods and how it changes, that just made me think of what happens in number blocks. And sometimes the way that they do transform into their new numbers when different blocks are added or multiples of them. And hearing you tell that story and hearing what Kit was saying and what Lucy and everybody else has been saying about the why are we doing this, for what reason, for what purpose, it just comes back to, I think with things like this, the story that we are using to try and help to tell the maths is so much more important. If we try and contrive something that we think is going to make it worse, we've lost them completely. So when it comes to something like division or inverse proportion or something like that you really have to think deeper about, I think the context we're using and, you know, the hinterland knowledge that we're bringing into it there is so much more important to consider than if we're just putting questions together for multiplication. And maybe I've been a bit, I'm throwing that away a bit, maybe a bit too much about multiplication, but I wonder if it's easier to come up with a story about multiplication than it is about division that we can really follow and understand. Or is that just me?
Well, I was just going to say, when I was looking this up, I remembered that there were generally two models of division that we've talked about, the partitive and the quotative. I remembered there was supposed to be 4 at multiplication, but I couldn't remember what they were. And so I had to look them up again. And it is interesting to me that wasn't intuitive. There would be more. And these are kind of semantic structures. They're not necessarily, we wouldn't necessarily all agree that they're different things. But there is a suggestion that there are 4. So equivalent groups, 2 tables each with 4 children, multiplicative comparison, so that's 3 times as many boys and girls, rectangular arrays, 3 rows of 4 children, and interestingly, we haven't talked about this properly, Cartesian product. So the number of possibles, and everyone knows this is my favourite thing to talk about, so I'll be quiet for a bit. But I think that's really interesting, that in many ways there are more ways to model multiplication in more difficult ways, actually, than division.
What was the 4th one again? I'm sorry.
Cartesian product.
I'm not familiar with that.
So the example given here is the number of possible boy-girl pairs. I hate that example, it's horrible, but it's a combinatorial model. Essentially the multiplication principle of combinations. So yeah.
Jen, I'm going to bring you in here because you've been quiet for a while now. Have you got any thoughts on any of this stuff that we've been talking about in terms of models for division, or in terms of this thing that Mr. G was talking about earlier around this misconception of switching the numerator and denominator, or the dividend and the divisor?
Well, it's a couple of sort of bits that I use in the classroom. One thing that I found, particularly GCSE, when students are doing trigonometry, and you've got something like sine theta is opposite over hypotenuse, substitute and rearrange, and I think you come up against that same difficulty. And again, I think it's always a good idea to then go back to a known fact. And that I found in terms of a takeaway into the classroom is I give them a known 12 divided by 4. I ask them to cover up the number that is the variable that they want to know, and to use the common sense of what they know between the other 2 numbers to rearrange that equation, as it were. So I think it does create difficulties, and I do agree. Way more there is more to the multiplication. It's a good break, really, me. But when it comes to the So I think relating it to a known fact really help. And I love the idea of using the context of the world and knowing about the world. And I understand where Lucy was coming from in terms of the blocks of wood, and what's it for, what does it mean? And we come across that when we're doing lots of problem solving, and you're going to this laundrette, you're going to that laundrette, and you think, well, I don't care, so I've got a washing machine at home. This problem means nothing. So again, one of the things that I found students never miss a beat on is sharing money. And if you're, if I've £100 and I'm going to share it with, you 3 students and me, how about I get it and you get, the rest? Is that fair? And of course it is. So I think that there tends to be a leap in the kind of understanding when you start sharing money and you start talking about whether that's fair or whether that's not fair. How much money do you want? You have to take £1 and I'll take 99, and it's just I completely agree that the real world can really accelerate that levels of, and it accelerates the interest that the students have in what you're talking about as well.
I agree totally there, Jen. One of the best ways I've ever taught ratio to a year 11 group that had never really grasped it was telling them that each 2 different people had worked different hours on a market stall, but they made this much money. Wow. They made sure that money was the person who worked more got more money, and the person who worked less got less money. Their sense of fairness often really helps with division, because, well, actually, if I've got this many parts, if this person's worked for 5 hours and this person's worked for 7 hours, they shouldn't get the same amount. That's not fair. But maybe that word fair is also an issue, because we use it to mean equal sometimes, and we don't always mean equal. A lot of our language comes back to how do we use it, at which point.
Lucy, I can see Lucy's eager to dive in because we've used one of her trigger phrases.
No, I was really interested to hear Jane talking about money, because I've been looking into that quite a lot. And what's particularly interesting to me is the idea of fairness in young children is well documented, and sharing money is a really good one. But I'll tell you what's interesting: sharing time, because you cannot share it like you share other measured quantities. And if you say to children, how are we going to share turns over time on something, there's so much cool maths in that, because first of all, it's the idea that you have to take turns, and what that means, you've actually got inherently odds and evens there. It's never fair, because at some point you don't always know how much time you've got, you don't always know how to divide that time, you can't repeat measurements of time goes past in a linear way. So I think the concept of division of time is really, really underrepresented in curriculum and under researched. It's so interesting. And knowing from my own kids, like, we have this very complicated algorithm for who gets to play Minecraft for X amount of time, because some children get up before others in the household. They have a certain amount of time after the adults get up. What happens then? How long should we let them carry on? If one of them gets 1 minute more than the other one, they get annoyed, but equally they should be able to finish the thing they're working on. It's not fair to just do it by time. So I think it's fascinating stuff.
Lovely. So we've been talking for over an hour. We're going to have to wrap up soon. Couple of bits. This one came in from whoever was tweeting on behalf of the Glow Maths Hub. I don't know. Why would we want to ban the word over? Kit, go for it.
I do. And I say, I do, because when kids read a fraction 2/3, all it does is describe how it looks. You've told me what to write, but you didn't tell me anything about what it means. And so the students will often lose the fact that division bar, that fraction bar, that it's division. And so I've started actually describing the fraction or the division symbol that looks like that with the line and the 2 dots as training wheels. They're training wheels for fractions. And when we take a fraction, right, and we have like our numerator and our divisor, then those are replacing the dots in the division symbol, and helping kids get this idea that, like, oh, we're taking off the training wheels, we're putting our numbers into the fraction. It's been really transformative in them remembering, oh, I'm saying 2 divided by 3. that's what 2/3 means, because so often they come to me in middle school and they can describe it all the time, 1/2, 2/7, and they have zero clue that it's even related to division.
Jane, you wanted to come on that?
I think that ties back into something we were talking about earlier, that fractions are really hard because kids want to end up with a decimal. A fraction isn't an answer to a question. And I think that's mixed up with their understanding that fractions can be an instruction to operate. Do this thing, do 3 divided by 4, but they are equally the result of that operation. And that's like, who would ever write 3 divided by, with the 2 dots, 4 equals, 3/4. So fractions and divisions mixed up as...
But that's an interesting point in itself, isn't it? Because that would imply that fractions are not always division. That fractions are sometimes division.
Yeah.
Would it not?
Yeah. I'll go with that.
It's not a vinculum, it's an obelus, is the division symbol, and a vinculum has to go above a number. It's a fraction bar.
Yeah.
Sorry. I'm just saying it's not a vinculum.
What about this one now?
I was even just thinking about what Jane just said, of like holding on to that idea that like this symbol means do this operation. And you also have the fraction that means this is the result of it. I actually really wish that we taught in elementary school more often, because I think that kids struggle with algebra when you have an expression where it's like x plus 3, and suddenly they're like, well, that can't be the answer. Why not write stuff like, 2 + 5 = 3 + 4, where they see an operation on both sides and they get that sort of relationship meaning for the equal sign, not just, oh, it's an operation.
We're straying into notions of equality now, I fear and feel, and we definitely do not have time to explore the concept of equality, given that we've already done this. So, I want to finish off. Karina is just going to ask one quick question, but she hasn't yet put what that question is, so hopefully that will come in. I want to finish off just with a quick one from everybody, which is, well, what's the solution then? What do we do about this fact that division is so hard? And obviously, you're not going to be able to expand on... Oh, no, Karina's coming first. So what do you think of the division algorithm? Does it still serve a purpose? So obviously, I think we've talked about that quite a little bit. I don't think we reached consensus on whether it shows purpose and whether it serves purpose. But then I don't think we would achieve consensus, and it would be a rather boring world if we did, to quote Mark McCourt. So yeah, I'm gonna say to Karina, if you pick up some of the bits from earlier in the discussion, you might hear a bit about the division algorithm there. But go on, one sort of comment, one sort of overarching idea about something we might do, or something we might say, or something we might show to start to redress this idea with division.
I'll go.
Go on, Lucy. We'll work our way across the list. So, Lucy, go.
I think having argued quite robustly with Kit, I do agree with him about the area models and the arrays. And for me, I've been working on this problem for a while to think about representations of division that would be more useful. And there's 2 things that come to mind. One is, if we think about this idea of an area model or an array, folding it, I find that really useful. Think about different ways to fold a rectangle, and that's a really powerful model for division for me. And then the second one is, if we go back to kids wanting to share things fairly and equally, Mike Askew has this brilliant task, which is about chocolate bars on chairs, where he has 3 chairs and he puts chocolate bars where they have, chocolate bars, you have discrete chunks, and kids have to go and stand behind the chair with which they'll get a share of that chocolate bar. And it is brilliant. And the idea of thinking about different ways to divide things depending on fairness absolutely has to be key to this, I think.
Thank you. I'm sure I only said one thing, but I'll let you get away with two.
Well, what are you going to do?
As this whole idea of having conversations was your idea, I'll let you get away with two. But the rest of you do not even think about taking that same liberty. Rhiannon?
For me, I think it's about precision. I need to be a lot more precise in the vocabulary I'm using and making sure that I understand the vocabulary that I'm using to help me explain what's happening with students. Because if I can understand the vocabulary, then I will hopefully have a deeper understanding of what it is that I'm working with as well. So that's what my focus is going to be.
Yeah, for me, it would be, I'm going to just be really looking at relationships, so comparative. So how we're comparing multiplicatively and therefore the inverse of comparing. Still haven't got a word, have we?
Let's say it now. I'm drawing a line in the sand. It's a word and we're all going to
Visibility.
No, I like it's rationally, to be fair.
Rationally. I think that's it. I actually think that it is that relationship with ratios, and it's going back to the 1 to n, and that therefore that is the multiplicative relationship. And those relationships, that's me.
So precision on language, focus on relationships. This is not just for us, of course. This is how we go about fixing the problem more generally. So, Jane?
I think a common thread in lots of the possible solutions we've talked about is just experience and exposure to different representations, language of, models of, measuring, all of these things, giving kids these opportunities to experience these things so that becomes part of their narrative around division.
Spot on, brilliant. Thank you, Kit.
I think that the stories that anchor the division in the real world is really a key, and recognizing which stories are going to make the most sense is sort of vital, because some stories make a lot of sense for one situation, but not for all of them. And I think it's about finding that story that really works for more of them.
Thank you very much. And Jen, finally again.
I agree with quite a lot of what's already been said. I think I've written down that I think that improve mathematical fluency and make the repeated link the multiplication and division facts, certainly in the younger year groups, so that again it's going back to language that we would maybe use it, but going back to the fact that those do. One thing that certainly some of the lower ability classes that I've taught do division as a repeated subtraction, as opposed to having that mathematical fluency. I think building that up certainly in the earlier years. One thing that's been said in this meeting that I had never crossed, and I'm surprised, the bus stop is 2 sides of a rectangle. Hasn't been on my radar until tonight, so thank you. And I will start taking that away and using that in the classroom. And then I agree with, again, what's been the nation of areas of the world. And like little kids know that when they run faster, that time is quicker. They know that the time is a number, but going through that and using that in the class, I think would be an idea to use to ensure that the students get that sort of consideration.
And I agree with all of that. But no, I do think, I think it all comes together there, doesn't it? I think it comes together with the stories, with the models, and the models being able to link to the stories. And as Lucy was saying, kids being able to draw their own models for the story of what's going on, and to show them and to show what their thinking is for what's going on. And I think within those stories, that the use of the language, I think, is going to be sort of important to being able to tie what's going on in the story to the correct mathematical language at some point, and also sort of like Sharon was saying with the those different relationships as well. So I think that's sort of
one thing that I really hate the concept of correct mathematical language, agreed mathematical language. If you think.
Yes, I take your point, Lucy. Thank you very much for correcting me, and I agree with you.
I also want to say the reason I don't like rational as an adjective is it's been used to deplatform and devalue what women say for many, many years, and that's why I don't want it to be used in place of multiplicative as a relating to division word.
That's a really good point. Thank you for that.
Yeah, I think we can all agree and take that on board. So we will go with divisibility then, and we'll go with that one instead. Guys, thank you very much for joining us. These conversations we've only had 2, and they've both lasted over an hour at this point. Although I'm still blaming the dogs on the last one lasting over an hour. To be fair, thank you to everybody as well that has come in for the messages. To Mr. G, Gaskell, to whoever runs the Glow Maths Hub thing, to Julia for all her comments in there. I know we didn't get to them all, Julia. To Vicky and to everybody else who's been watching. Thank you very much for bearing with us. Thank you again to all of our guests for joining us, and we will hope to see you again in the future. Thank you very much, and good night for everybody except Kit, who it is for good